Alrighty, in this video we're going over the practice test solution for quadratics. Make sure you've got your calculator and your formula sheet as well. Alright, first question, we need to find the y-intercept. Pretty much what you can do is just read off the y-intercept as this last number, y is minus 21. Or if you want, you can sub in x equals 0. So it's 0 squared plus 4 lots of 0 take 21. Hey, it's minus 21. If you want, you could also graph it on your calculator and then trace at 0. I am going to do that just because we'll need it a little bit later in the question. So let's delete out that old graph, and we're looking at x squared plus 4x take 21. Alright, we draw that graph. The window is pretty terrible. You can just hit standard here to put it back to your normal window, and there we go. And I might need a bit lower, so I'm going to go down to this y value and change it to maybe minus 30, something like that. There we go, it looks pretty good. Find the x-intercepts of the quadratic algebraically. So if you ever see this word or this word, it means you need to show you're working. You can't just get them off the calculator. But you can go g-solve and root to verify what they should be. So they should be minus 7 and 3. So that's sort of what we're expecting. But basically the way that you're going to do it is you're going to look at this, 4x take 21. You're trying to set y equal to 0 to find the x-intercepts. That is actually on your formula sheet, sort of up there. And then we're going to look at sum and product. So we need two numbers that times to give minus 21, and they add to give me 4. So if you think about this for a while, those numbers are going to be 7 and minus 3. Fun fact, they're the flipped versions of what those x-intercepts are. So you're going to have x plus 7 as a factor and x take 3 as another factor. So if we sort of look at this, you're going to have x plus 7 is 0. So x is minus 7. Here you're going to have x take 3 is 0. So x is 3. Now if it's showing show you're working, you might want to say like sum and product, something like that, just to show that you know what you've done. Find the coordinates of the vertex. So the vertex is right in the middle of the two x values. So basically, we've got minus 7 plus 3, and then if we halve it, you're going to get minus 2. And then the y value is just subbing in minus 2 to that quadratic. So you got minus 2 squared plus 4 lots of minus 2 take 21. So that's going to give you 4 take 8 take 21, which is going to give you minus 25. So the coordinates are minus 2, minus 25. Or you can use your calc, and if we've got it graphed already, you can just go g-solve min, and that's minus 2, minus 25. Alright, I use this information to graph the quadratic, so we're just going to pop on that vertex that we've got, minus 2, minus 25. We'll pop the y-intercept on there, minus 21. There it is. We're going to put our two x-intercepts on, so that's minus 7 is one of them. And it is 3. And then if we sort of connect up all those pieces, we'll get a lovely quadratic shape. Make sure there's arrows on your graph, and make sure you label it with the equation. There we go. All right, next we need to find the equation of this quadratic. This is the x-intercept form, so be aware there are two different forms for quadratic equations. These are the two forms here. So there they are. We're going to use the bottom one. So we're looking at a, x take 2, that's one of the x-intercepts, is 2, and x plus 3. So then we can sub in 0 minus 6. So we're going to have minus 6 and 0 for the x's. So 0 minus 6 is being subbed in. So that's going to be a, lots of 0 take 2, and 0 plus 3. So minus 6 is a times minus 2 times 3. Minus 6 is minus 6a. Therefore, a is 1. So our equation looks like this. 1 lot of x take 2, x plus 3. Use technology to state the coordinates of the minimum. So this is going to be very similar to what we did before. So we'll just go up here. I'm going to be looking at x take 2 and x plus 3. I'm going to draw that. There it is. Probably not a bad idea to go g-solve root and make sure that they're matching. So we have minus 3 and crosshair is 2, so that's good. And if we go draw it again and we go G-solve, actually one other thing we should check, trace at 0 is -6, so that's the y-intercept, that's good. And we go G-solve min to get -0.5 minus 6.25. Cool. Find the equation of a quadratic which has that. So this is the other form of the quadratic. We're looking here at vertex form. A x take b squared and then b is going to be that x value, so 4 and -3 for the y value. And then we're going to sub in that point that we want. So the y-intercept is 5, and that happens when x is 0. So a lots of 0 take 4 squared take 3. So 5 is a times 16, because that's -4 squared. So 5 is 16a take 3. Therefore, if you add 3 to both sides, you're going to get 8 is 16a, or in other words, 16a is 8. Therefore, a is going to be 8 over 16, or a is a half. Cool. So we're going to get y is half x take 4 squared take 3. Now, how do we know that we got that right? Well, we can actually graph that. So we'll look at this. I'm just going to use 0.5 instead of a half, but then we've got x take 4 take 3. If we draw that and we go g solve min, we've got 4 minus 3 is the minimum there. If we look on the graph as well, we can look at that y-intercept. So trace at x is 0, you get y is 5. So it is correct. All right, fully expand and simplify. So we've got to expand that minus 3x in to get minus... Actually, I might start this question just by writing it like this. So that equals minus 3x squared. And then 2 negatives give us a positive. 3 and 4 is 12, and you get an x there. That's as simple as that's going to get. Then we've got here, so you leave the 5 out the front. So we're going to get x squared. We're then going to get take 3x. We'll get plus 2x. And we'll get take 6. So this is x squared take x take 6. Which if we expand the 5 into everything, there we go. All right, for each of the following quadratics, find the exact x-intercept. So no calculator here. Now this one here is already factorized. So we're going to have x take 10 is 0. That would tell us that x is 10. And here we'll have 3x plus 3 is 0. So 3x is minus 3. So x is minus 1. It's 3 over 3. So those are the x-intercepts. Here it's the same thing. It's just got the constant out the front. So x is 4, or 2x plus 1 equals 0. So 2x is minus 1. X is minus a half. I really want to point out, you could actually graph these and find the x-intercepts too. You get the right answers. Now here, if we can, we want to try and use sum and product. And then if that doesn't work, that's where we use the quadratic formula. So can we think of two numbers at times to give 3 and add to give 4? Yes, it's 3 and 1. Therefore, y is x plus 3, x plus 1. And that comes from sum and product. Therefore, 0 is x plus 3, x plus 1. Therefore, x is minus 3, or x is minus 1. Those are your two x-intercepts there. All right, this one here, you can try it. Times to give 6 and add to give 4 won't work. So we're going to use the quadratic formula here. So if we look at the quadratic formula, a is 1, b is 4, c is 6. Quadratic formula is on your formula sheet. So we'll just have a look for that down there. There it is. Right, now I can just put it into the quadratic formula. X is minus b plus or minus root b squared take 4ac over 2a. So it's going to be minus 4 plus or minus square root of 4 squared take 4 times 1 times 6. All over 2 times 1. minus 4 plus or minus root of 16 take 24, and you might spot an issue here. That's going to give you root of minus 8. So as discriminant is less than 0, no solutions. So we could say no x-intercepts. If you graph it, it will look something like that, so it won't cross through the x-axis. And I really want to point out that yes, you could graph it and find the x-intercepts, but if we go into our equation mode and go F2 for polysolve, degree 2, you can just enter the coefficients, 1, 4, 6. Now, I've got my calculator showing these weird solutions with I, but depending what your settings are, you might say no solutions, or if you see these really messy ones with I's, then that also means no solutions. We'll find out what I is a little bit later. All right, this one here, there's a couple ways we can do it, but probably the easiest way is just to try the quadratic formula. A is going to be minus 4, B is going to be 24, and C is going to be minus 36. And I'm actually going to preempt here what we're hoping it might be. So minus 4, 24, minus 36. And if we solve that, it looks like we might get this solution. So let's see what we get from the quadratic formula. It is also possible to sum and product this, and technically it's easier, but it's not entirely obvious. Well, like first you have to pull out a common factor and it might get a bit messy. So if you're not sure, just jump straight to the quadratic formula. So that's going to give you minus 24 plus or minus square root of 24 squared, take 4 times minus 36, all over 2 times minus 4. So if we keep going with that, this square root we can just work out directly. You can chuck that in your calculator. So we'll have a look at that. Menu, graph. So we've got 24 squared, take 4 times minus 4 times minus 36 is 0. Cool. Which actually should hopefully make sense based on what we saw on the calculator, because the calculator said there'd be a double solution at 3. So that's the only x-intercept. So if the other one here looked something like that on the x-axis, then this one here, it's upside down because that number's negative, but it'll just touch the x-axis. Cool. All right, next one. So the first thing we'll probably want to do here is go into menu polysolve and just see what that solution is going to look like. So it's degree 2 because it's a quadratic. It's the highest power of x is the degree. Solve that. Cool, so you get those solutions. 3 plus or minus root 41 over 8 is what we're expecting. There's a pretty strong indication we got to use a quadratic formula here. A is 4, B is 3, C is minus 2. We can plug in the quadratic formula. That's going to give us minus 3 plus or minus square root of 3 squared, take 4 times minus 2, all over 2 times 4. Minus 3 plus or minus square root of 9, yeah, that'll be a plus, 32, all over 8. So that's going to give you minus 3 plus or minus square root of 41, all over 8, which hopefully, hey, that's what our calculator said, so that's good news. So there's our x values. If you want to be extra fancy, you can say x is minus 3 plus root 41 over 8, or minus 3 take root 41 over 8. But I won't penalize you if you just leave it like that, that's also fine. But there are two solutions. All right, I've got a football being kicked here. There's the equation. I better graph it. So there we go. Minus 4.9. We have to use x instead of t. And then plus 14.7. If you're ever dealing with these projectile motion problems, that number minus 4.9 is always the same on Earth due to gravity. And then the 14.7 is, you know, the initial speed that the ball was kicked up at. So we're going to graph this function. Probably what we'll want on the graph is some of our key features. So how long will it take for the ball to hit the ground? They would be talking about the x-intercepts. So we want to make sure that happens at 3. So maybe on my graph, I'll have this kind of scale. And we know the graph is sort of going to come through 3. Like that. And it probably wouldn't hurt to have our maximum on there. G solve max, 1.5 and 11.025. So what I might have to do is go 2, 4, 6, 8, 10, 12. And it was at 1.5 and 11. So probably sitting about there would be the maximum. T, H. Now, T has to be in seconds, and H needs to be in meters. We need a graph at H equals minus 4.9 T squared plus 14.7 T. How long will it take for the ball to hit the ground? 3 seconds. You can tell because it's a 1 mark question. When does the ball reach its maximum height? So the max that we just figured out on our calculator was this. 1.5 and 11.025. So max height at 1.5 seconds, and the height is 11.025 meters above the ground. Now, technically here, because like position graphs start at 0, we can have a dot there and an arrow coming off the end, but do make sure you have an arrow. And I might even mark it 1.5, 11.025. Cool. All right, here we've got this sheet pen. So we're going to let x be the length. So there's x there. Explain why the width is 200, take 2x. So length plus width is 200, and I might just say given fence length is 200 meters. Therefore x plus w is 200. Therefore 2x plus w is 200. Therefore w is 200, take 2x. Now the area is going to be length times width. Now to show that question, so we're just going to go area of, now I might actually put back up here, total length, just to make that extra clear. Area of rectangle, therefore the area is, the length is x and 200, take 2x. And this is going to be from A. All right, then last step to get the formula we want, you just expand. So you're going to get 200x, take 2x squared, and since it's a show that question, I'm just going to write expanding there. And that matches the formula thereafter, which is good news. Next bits, we're just going to be graphing it on the calculator. So if you couldn't answer part A and B, you can still continue. That's really important to note here. So I'm just going to go into graphing mode there, type out the equation that we've got, hit draw. Looks kind of terrible with the window, so let's see if we can figure out what this window should be. We've got 200 meters of fence, and that's, the x value is essentially the length. Now, technically the biggest x could be is 100. Now let's suppose you didn't spot that, 200 will do, because the window doesn't have to be super precise. And if we're thinking about area, let's just see, if x was 100, maybe about 100 times another 100. Actually, that'd be way too big. 100 times 10, something like that. Let's just try 1,000 and see what works. Because window is really trial and error. You can see we tried 1,000 there and we're missing the top of the graph. So let's try instead 3,000. All right, still missing the top of the graph. So maybe let's just try 10,000. Cool. All right, so that's a nice little shape. I want to be really clear, the y-axis here is the area of the pen, and the x-axis is this thing we've called x in the question. So find the values of x which would make the area equal 4,800. Shift G solve across x cal 4,800. X is 40, or x is 60. And this will be in meters because the sheet pen is measured in meters. Wonderful. All right. Find the maximum possible area of the pen. So Shift G solve max 55,000. So max area is 5,000 meters squared when x is 50. And basically what it's going to look like, let's see, so it's the top wall there that is already existing. If x is 50, then the other side is also 50. And really importantly, the width is 200 take 2x. So the width is going to be 200 take 2 times 50, which is 100 meters. So that's what the width is there. All right, use the quadratic formula to do this. So A is 1 in this case, that's the coefficient there. B is -1, C is -1. X is minus B plus minus square root B squared take 4AC over 2A. So that's going to be -1 plus or minus square root of -1 squared take 4 times 1 times -1 all over 2 times 1. So that's going to be +1. This is going to be 1 plus 4 in here. And this is all going to be over 2. So that's 1 plus or minus square root 5 over 2. This is called the golden ratio. Let's find an approximate value for it. So that is going to be, if we just go into normal calculator mode, the plus version is the golden ratio. So that is 1 plus square root of 5 all over 2. And you set S to D, so 1.618. All right. You can then measure these pictures with a ruler. So if we measure this one here, now this will absolutely depend how far you are zoomed in, but what I'm getting with my ruler is 3 centimeters, and B I'm getting is about 4.6 centimeters. And then I'm just going to make a note here, it depends on zoom, because you might get different numbers, but the point is the ratio should be the same. So if I do 4.6 over 3, I get 1.53. And then if I do this one here, B in this case is 3.6. And A in this case is 2.4. So we get that roughly equaling. So the point is that basically this sort of equals the golden ratio when you work it out. All right, we got this little bonus question here. So I basically just want to point out to you the golden ratio is really cool and it comes from solving a quadratic, but it goes all over art and all over nature. You can even find it in like human DNA and stuff, golden ratio. And the point of this is like these numbers are supposed to be pretty close to that golden ratio there. So this situation here, basically, if we work out the big over the small lengths there, then they should be the same in both the big there and the small there versus the red one, big and small, just like that. All right, so we go with this equation, well, sorry, this one here. X is A over B first. So therefore 1 over X is the same thing as saying 1 divided by X, which is 1 divided by A over B, which is 1 over 1 divided by A over B, which is 1 over 1 times B over A, which is B over A. So that's why that one's true. It's sort of like dividing fractions. Hence rearrange that. So we can start by going A plus B over A equals A over B. Split the left, A over A plus B over A is A over B. And then you're going to get A of A is 1, b over a is 1 over x equals x. So this one here, I might actually just say, is from a, and the fact that a over a is 1. And therefore, if we times everything by x, x plus 1 is x squared, times x to both sides. Therefore, 0 is x squared, take x, take 1, after we rearrange. So if you solve that quadratic, you get the golden ratio, and that's much like what we solved up here, which is pretty cool. So it comes from this rectangle and the fact that that's a square on the left-hand side. It can also come from the Fibonacci sequence, if you're familiar with that, but it's good fun.